Imagine standing on a world 4 billion miles away, where the sun is nothing more than a brilliant pinprick in a twilight sky, offering absolutely no warmth. You would expect it to be cold, but what if I told you this tiny dwarf planet is actively running its own cosmic refrigerator? It is cooling itself down, using nothing but the haze in its own atmosphere.
It sounds like science fiction, but the James Webb Space Telescope recently confirmed that Pluto is doing exactly that. It is actively refrigerating itself, keeping its upper atmosphere about 30 degrees Fahrenheit colder than any of our planetary models predicted. Instead of acting like a thermal blanket, the hydrocarbon haze in Pluto's atmosphere acts like a giant radiator, absorbing what little sunlight it gets and immediately venting that energy back out into the void of space.
It completely turns our understanding of planetary climates upside down. When we look at this discovery, it is not just a win for astronomy, it is a fascinating case study in how we conduct deep space exploration. If we look at this through a strategic lens, say a SWOT analysis, the strengths here are obvious. We have the incredible infrared sensitivity of the Webb telescope, which finally allowed us to isolate Pluto's thermal signal from its massive moon Charon. But the weaknesses are equally massive. We are relying on remote observations because sending a physical spacecraft out there takes a decade, and we only get one shot as it flies past at 30,000 miles per hour.
Exactly. The New Horizons flyby in 2015 was a masterpiece, but it was a single snapshot. Webb gives us a continuous capability, which aligns perfectly with the scientific community's broader mission and objectives. If we break down the strategic alignment using the MOST framework, the mission is to map the chemical evolution of our solar system. The objective is to identify prebiotic chemistry in the Kuiper Belt. The strategy is to leverage space-based infrared observatories to bypass the physical limits of space travel, and the tactics involve targeting Pluto during specific orbital windows to analyze its atmospheric chemistry without the interference of Charon's thermal bleed.
It is a brilliant workaround for a massive logistics problem, but the science itself gets even stranger when you look at the relationship between Pluto and Charon. They are locked in this tight gravitational dance, orbiting a shared point in empty space. And they are actually sharing an atmosphere. Pluto has been slowly leaking methane and other light molecules into space for billions of years, and Charon has been catching them.
It is a literal cosmic handoff. Charon's poles act as a cold trap. During its decades-long winter nights, the escaping methane from Pluto drifts over, freezes solid onto Charon's surface, and then gets blasted by ultraviolet radiation when the sun finally returns. This chemical cooking turns the frozen gas into complex organic molecules called tholins, staining Charon's poles a deep, reddish brown.
Which brings us to a really compelling part of this intelligence report, the macro-environmental factors. If we apply a pestle analysis here, the political and economic dimensions of this research are highly complex. Politically, space exploration is often driven by national prestige. But economically, funding a mission that takes 15 years to yield results is an incredibly tough sell. Socially, the public is fascinated by the search for life and the origins of organic molecules, which Pluto is actively manufacturing. Yet, technologically, we are right at the limit of what our instruments can detect.
The legal and environmental aspects are also fascinating. We have strict planetary protection protocols to ensure we do not contaminate these pristine environments, but the sheer hostility of the Kuiper Belt environment makes contamination highly unlikely anyway. If we transition to a spear analysis, looking at security, politics, economics, aerospace, and resources, the aerospace and academic value of this data is off the charts. We are looking at a natural laboratory that has been running a prebiotic chemistry experiment for 4 billion years. The organic molecules raining down on Pluto are the very same building blocks that some scientists believe seeded early Earth.
It makes you realize that Pluto is not just a dead rock. It is a window into our own past. But the resource allocation problem is where things get tricky. Why are we spending billions on Mars and Europa while Pluto gets left in the dark? We can actually use game theory to understand the logic behind this funding dynamic. Think of it as a game played between space agencies and government funding bodies. The payoff matrix heavily favors short-term, high-certainty missions. A mission to Mars or the Moon offers quick political wins and rapid data return within a single administration's life cycle. A mission to the outer solar system is a high-risk, long-term bet where the players who fund the project will likely be out of office long before the spacecraft ever arrives.
So the Nash equilibrium in this funding game leads to a systematic underfunding of the outer solar system. Agencies choose the safer, closer targets, leaving worlds like Pluto to be studied from afar. And that is a shame, because the geological complexity we are seeing is mind-blowing. We have evidence of cryovolcanoes, mountains like Right Mons that stand 13,000 feet tall and erupted not with molten rock, but with a slushy mix of water, ammonia, and methane from deep underground.
And then there is the theory of a subsurface ocean, buried 100 miles beneath the ice crust, kept warm by radioactive decay in Pluto's rocky core. If a world that small and that cold can maintain a liquid ocean, it suggests that liquid water and the potential for life might be far more common in the outer universe than we ever dared to imagine.
It challenges the very definition of a habitable zone. We used to think you had to be close to a star to have liquid water. Pluto suggests that you just need a rocky core and a thick blanket of ice. It changes the entire equation for astrobiology.
It really does. And if you enjoy these kinds of deep, strategic dives into the mysteries of our universe and the forces shaping our future, you should check out the sponsor of today's episode. The New Sentinel is a podcast dedicated to providing in-depth discussions and deep dives into a wide array of topics. From the glitz and glamour of pop culture to the strategic intricacies of military operations, they cover it all. Each episode is thoughtfully crafted to offer listeners a comprehensive understanding of the subject matter, featuring expert interviews, detailed analysis, and engaging storytelling. Whether you are a pop culture enthusiast or someone with a keen interest in global security, the New Sentinel has something for everyone. Tune in, view, comment, and post an inquiry to stay informed and entertained.
It is the perfect place to continue the conversation, especially when we look at the sheer scale of what we have yet to explore. Pluto is just one object in the Kuiper Belt, which is hundreds of times larger than the asteroid belt between Mars and Jupiter. There are hundreds of thousands of similar icy worlds out there, and we have only ever photographed 2 of them up close.
It makes you wonder what else is waiting out there in the dark. If one dismissed dwarf planet can hold this much complexity, what are the others hiding? We are standing on the shore of a vast dark ocean, and we have barely dipped our toes in the water. The data will keep trickling in, and with every new image from Webb, the universe gets a little bit stranger and a lot more interesting.